All right, so chapter 10.2, if you look at the actual title of the section, it is entitled Using the Fundamental Counting Principle. The fundamental counting principle is when we can do what we just did a moment ago. We can draw blanks and list out the number of ways each blank can occur and then multiply them together, which we could have done instead of drawing out our pictures on some of our problems that we had last time. So the question is, when can I do that and when can I not do that? And the answer is found in your textbook on page number 534, where you will find a green box that says Uniformity Criterion for Multiple Part Task. Okay, so let's read what that says and let's try to make some sense out of it. It says a multiple part task is said to satisfy the uniformity criterion if the number of choices for any particular part is the same, no matter which choices were selected for previous parts. What are you saying, Mr. Black? Well, somehow this notion of what your book is calling here a uniformity criterion is going to play into when we can multiply to find the number of ways a series of events can happen and when we can't. Now, to see how it's going to play into that, let's go down here and read the fundamental counting principle. The fundamental counting principle is what allows us to draw blanks, and let's see what it says. It's at the bottom of that same page. It says, when a task consists of k separate parts and satisfies the uniformity criterion. So that's how it's going to play in. Then the first part can be done n sub 1 ways, the second part can be done n sub 2 ways, and so on through the kth part, which can be done in n sub k ways. Then the number of ways to complete the given task is given by the product, and you got this product. Now, what in the world does all that mean? That's a lot of words, and it sounds technical, and it's kind of mumbly and jumbly. What is it saying, Mr. Black? It's saying that if we satisfy the uniformity criterion, then we can draw blanks for each part of our task, each part of our multi-part task, and we can fill in the number of ways each blank can occur and then multiply those together. And that'll give us the same total that we got by using a tree diagram or such as that. Now this is really important because most of our tasks that we had in our last assignment were like 3-part tasks, maybe a 4-part task. If you had a 10-part task, your tree diagram would get so large, there would be so many numbers of possibilities, you could literally spend the rest of your life making your tree diagram. So we need a different approach on a lot of these problems. So let me show you a real simple problem to where we could apply this concept. Okay, so let's say you go to supper tonight and you go out to eat and you go to this real basic restaurant. Okay, and at this restaurant you have your choice between 3 different types of salad. Maybe you can have a house salad, a Caesar salad, or some other kind of salad. You can have 4 choices for your main dish. So maybe you got roast beef, fried chicken, steak, or lobster tail. I'll go with the steak, please, medium. And then let's say you have 2 choices for a dessert. And let's say the question is, how many different meals could you make? Okay, so if this problem fits the uniformity criterion, then we can draw blanks. So I'm going to have to talk us back through what that uniformity criterion said. And what we can do with each blank is fill in how many ways it can occur. So there's 3 different salads I could choose. So there's three ways the first part of our task could occur. It could be Caesar salad, it could be regular salad, it could be the third kind of salad, whatever that was. Three different ways. Now, here's how you know if you meet the uniformity criterion or not. Here's what it said. It said if your next choice is the same regardless of what your previous choice was, then it fits the uniformity criterion. So let me ask you, we said we had 4 choices for the main dish. Roast beef, chicken, I don't remember what my other 2 were, lobster tail and steak, I think it was. Okay, now, do I have 4 choices no matter which kind of salad I chose? Yes, I do. So in this case, I do meet the uniformity criterion because it's 4 choices here, regardless of what I chose first. If this problem would have said like, if you choose Caesar salad, then you must have the steak, then I'd still have 3 choices for the salad, but then the number of choices for the main dish would depend on what I chose for the first dish. If I chose regular salad or the third kind of salad, I'd have 4 choices, but if I chose Caesar salad first, I'd only have 1 choice for the second. So it is different depending on what I chose first. That violates the uniformity criterion. So it has to be the same regardless of what you chose on the previous blank. So here, regardless of whether I choose roast beef, chicken, steak, or lobster tail, I still have 2 choices for dessert. So I'm still meeting the uniformity criterion. So obviously the number of meals that I could make would be 3 times 4 times 2, or 24. So we're going to look at several examples here in this section where we can apply this notion. Now, what did your book call this? They called this the fundamental counting principle. Okay? But Mr. Black just calls it drawing blanks. So we're looking at when we can draw blanks and when we can't. Okay, well let's practice a few problems and see how it fleshes out then. Turn to page 535 and let's look at example 1. Now let me say that these problems, the working out of these problems is not difficult. You're multiplying 2 numbers together, whoopee-doo. But sometimes the setting up with these problems can toy with you a little bit. So you just got to slow down and think and stick to the principles that we talk about as we move through the chapter. Example 1 says this. How many 2-digit numbers are there in our base 10 system of counting numbers? How many 2-digit numbers? Okay, well if I got 2-digit numbers, that's a 2-part task. Let's see if we can draw blanks. Now usually it's going to be obvious if you can't draw blanks. You're going to hit a snag somewhere in the road. We'll illustrate that again as we move through the lesson here. So if I got a 2-digit number, let's think about the first digit for a moment. How many choices do I have for that digit? So think to yourself, what can that digit be? What can't that digit be? The first digit. 1 through 9, but it can't be 0, right? If the first digit was 0, then I'd have a 1-digit number. 0, 8 is just 8, right? So it can't be 0, it could be anything else. So there are 9 ways the first digit can occur. Then think to yourself, how many ways can the second digit occur? Yeah, I've got 10 now because it could be a 0. I could have a number like 80 or 30. So it could be 0 or 1 through 9. So there are 10 ways it can occur. So there are 90 different 2-digit numbers that we can make. Okay, now example 2, they're going to change that problem up on you just a hair. It says, find the number of 2-digit numbers that do not contain repeated digits. Okay, so I'm still looking at two-digit numbers. It's still a two-part task. Tristan and Summer, how many choices do I have for the first digit now? Let's go through our list. Could the first digit be 0? So that first digit, again, can be anything except 0. I can't have 0 in the first blank, so I only have 9 choices left. Now, let's put Summer and Tristan back together. Once I got a digit in my first digit, now if I can't repeat digits, how many choices do I have for the second digit? So think about it. I'm getting 0 back because the second digit could be 0. But I lost the digit, whatever the first digit is. If the first digit's a 3, I can't have a 3 second because that'd be repeated digits. If it's a 5, I couldn't have a 5 second. So what do I have? I went from 10 originally, now I'm down to 9 because I can't repeat whatever the first digit was. So I have only 9 choices for the second digit, which means there are 81 two-digit numbers without repeating digits. Okay, so let's keep the train moving here. On example 3, we're going to throw you a little bit of a curveball. So it's at the bottom of page 535. Let's take a look at it. It says, in how many ways can Club N of the previous section select a president and a secretary if no one may hold more than one office, and the secretary must be a man? So this is a little bit different problem than we did in the last section when we listed things out. Now the president has to be a man. So remember, our Club N consisted of Alan, Bill, Kathy, which I'll call Kath, David, which I'll call Dav, and Evelyn, which I'll call Eve. So let's do the problem just the way that it's written. It's a two-part task because I'm electing a president and a secretary. So my first question to you should be an easy one, but sometimes I don't see easy things, so I want to see if you see this or not. How many ways can I elect a president? 5 ways. It could be Alan, Bill, Kathy, David, or Evelyn. Now, earlier I said if you don't meet the uniformity criterion, then somewhere in the problem you're going to hit a snag, and that's what's going to happen now. Because the question then becomes, how many ways could I elect a secretary? And for most people, the initial gut feeling is 4. That may or may not be true. Okay? What did the problem say? It said that the secretary must be a man. So if I chose a man first, if say Alan ended up being the president, then I only have 2 ways to fill the secretary position, Bill or Dave. But if Kathy ended up being the president, or Evelyn, but let's say Kathy, then I'd have 3 ways of filling the secretary position. So I have violated the uniformity criterion because the second blank does not have the same number regardless of what the first blank was. So we crash and burn here. Okay, so if I was going to, one thing I could do is go back and list, like I did in section 1, figure it out that way. But not all is lost here. Flip in your book to page 536. There's a purple box at the top of that page that's going to give us a a principle that we can apply here, and that's going to be helpful. Here's what it says. Example 3 suggests a useful problem-solving strategy. Whenever one or more parts of a task have a special restriction, try considering that part or those parts before the other parts. So if we've got a restriction, we want to do the restriction first, or any parts that have a restriction. And the part that had a restriction on this problem was the secretary had to be a man. Okay, so let's see if we can rework this problem, considering the secretary first, and then the president, and then see if we get somewhere. Okay, now if the secretary must be a man, it has to be either Alan, Bill, or David, so I have 3 choices there. Once the secretary position is filled, it's going to be one of those 3. And do you see that now I'm going to have 4 choices left for president, regardless of who's chosen for the secretary. If Alan's chosen for secretary, Bill, Kathy, David, or Evelyn can be president. 4. If Bill's chosen for secretary, Alan, Kathy, David, or Evelyn. That's 4. If David's chosen for secretary, we have Alan, Bill, Kathy, or Evelyn. We have 4 regardless of what happens first. So now I fit the uniformity criterion, and I get 12. 12 different ways to have a president and a secretary if the secretary must be a man. So example 4 is going to be much like examples 1 and 2, except we're going to be looking at 3 digits instead of 2 digits. It's at the top, page 536. Here's what it says. How many non-repeating, odd, 3-digit counting numbers are there? Okay, so now we got to start thinking in this fashion. We know that if there's a restriction, we want to consider it first. So Katie, Robert, Chris, let's throw you guys all in together. The fact that I have 3 digits only puts a restriction on the first one. It can't be 0, right? Non-repeating doesn't really put any restrictions on me. What about the fact that I'm odd? Well, I mean the number is odd. I know you guys think I'm odd. That's okay. Okay. What about the fact that a number is odd? Does that put a restriction on any of the digits? Any of the 3 digits that we're going to have?
Yes.
Okay. So let's go to Katie and Chris. What has to happen to have an odd number? Say that again.
Take out the even.
Well, how do you know, if I say give you the number 58, how do you know if it's even or odd?
Last number.
You look at the last number, right? The last digit. 58 is even because the 8 is even. So the fact that this number has to be odd puts a restriction on the last digit, so we're going to have to consider it first. We also have a restriction on the first digit because it can't be 0, so we'll consider it second. And then the second digit is not going to have a restriction, so we'll consider it last. So let's go back to the 3 of you and ask you, how many ways can the first digit occur then?
5.
If you're not sure, Robert's saying 5, let's see if he's right. If you're not sure, just run through the list and ask, could it be that or could it not be that? Could an odd digit end in 1? Yes. Okay. Could it end in 2? No. Could it end in 3? Yes. Could it end in 4? No. Could it end in 5? Yes. Could it end in 6? No. Could it end in 7? Yes. Could it end in 8? No. Could it end in 9? Yes. Could it end in 0? No. So there were 5 yeses that I had there. So Robert's right. There are 5, an odd number has to end in 1, 3, 5, 7, or 9. So there's 5 ways it can occur. Class, you should know by now that normally there's 9 ways the first digit can occur because it can't be 0. But we also can't repeat digits here. So whatever the last digit is, the first digit can't be that. Okay? So we're going to have 8 choices for it. Now, without looking at your book, thinking through this problem, no repetition, how many choices do I have left now for the second digit?
8.
Okay, Chris and Katie. We have 10 digits to choose from, but we can't repeat digits, so the second digit can't be the last digit, and it can't be the first digit, otherwise I'd have repeated digits. You see that? So, therefore I started with 10, 0 through 9. I can't have either of the last or the first, so that leaves me 8 choices for the second digit. And if you take 5 times 8 times 8, you're going to get 320. So 320 different 3-digit numbers without repeating digits. Okay, now I want to make sure that you just understood that. So I'm going to give you guys a problem to work here, right there at your seat. So I'm going to pause my video again. I want to take a look at example 5. So let's start to go a little quicker now that we're getting a little better feel. Example 5 asks the question, in some states, auto license plates contain 3 letters followed by 3 digits. How many such license plates are possible? Okay, well, 3 letters followed by 3 digits means I would have a 6-part task. So I'm going to draw 6 blanks. Did it say anything about repeating digits? Didn't say anything about it, so now I can repeat all I want. Okay, so how many choices do I have in the first blank? Well, I'm picking a letter. How many letters do I have to choose from? 26. Now, since I can repeat the letters, then I also have 26 choices for the second digit, or second blank, and 26 choices for the third blank. Then it's followed by 3 digits. Well, now I'm not looking at 3-digit number. I'm just looking at 3 digits. So the first digit could be 0 or 1 through 9. And so could the second, and so could the third. So all of these 3 are going to be filled in with 10s. And if you multiply all those numbers together, according to your book, you end up with 17,576,000 different license plates that can be made. Okay, I want to look at one last problem with you out of this section. And it's example 11 over on page 540. And it says, Tricia Caruso is taking 13 preschoolers to the park. How many ways can the children line up in single file to board the van? Let me just tell you, it's going to be a bunch. It's going to be a bunch of different ways you can line up 13 kids or 13 things. So let's not try to do this problem. Let's try to do a simpler problem. What if I said, how many ways can you line up 3 things, 3 kids? Okay, well, that's a 3-part task, so let's draw 3 blanks. Let's say our kids are Alan, Bill, and Kathy. Okay, let's play the game again. Summer and Chris, how many choices do I have for the first blank, for the first spot?
3.
I have 3. Once a kid gets in the first slot, how many choices do I have for the second slot? I have 2. And once you got kids in each of the first 2 slots, then the last slot would be chosen for you, wouldn't it? So it'd only be 1. So 3 times 2 times 1 is 6. Do you see that if I would have changed this problem to 5 kids, that it would have worked out the same way? The first blank would have had 5 choices, the second blank would have only had 4 then, and the third we would have been left with 3, and the fourth we would have been left with 2, and the last one we would have been left with 1. 5 times 4 times 3 times 2 times 1, which I believe is 120. So there's a name for this notion of 3 times 2 times 1 and 5 times 4 times 3 times 2 times 1. It's called a factorial. 3 times 2 times 1 in math is called 3 factorial, which is denoted with an exclamation point. So this in math reads 3 factorial. It does not read 3!
Shouldn't be 13, not 3.
Yeah, well, we haven't got to our problem yet. I said we were working a simpler problem first. We're trying to get a feel for what's happening here before we go back to the 13. Okay, so 3 kids ended up being 3 factorial. 5 kids ended up being 5 factorial. So what do you think 13 is going to be? It's going to be 13 factorial. In fact, if you look in your book, at the bottom of page 539, it generalizes this notion, and it says if you have n objects, then you can arrange those n objects in factorial ways. So going back to example 11, how many ways can I arrange 13 kids? 13 factorial ways. Which means you have a lot of work to do on your calculator, 13 times 12 times 11, da 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 da, all the way down to 1. Or maybe you don't. Because most calculators will have a factorial function. So you're looking for something with an exclamation point. Now, if you have a graphing calculator, a TI-83 or 84, I can tell you that that function is in the math menu. So you're going to hit 13. The math menu is over here on the left-hand column. And then you have to go over to this PRB submenu. And see, number 4 is the factorial. Oh, I hit the wrong thing. Let me do that again. Okay, so it's going to be that ridiculous number there. What is that? 6,227,020,800. On other calculators, especially Texas Instruments scientific calculators, you'll find the exclamation point if you hit the PRB key. Anybody see a PRB key on their calculator? Okay, usually you can find it in there, and then for others you're just going to have to look for it. Okay, so the moral of this story is, the wrap-up of this section is this. We can draw blanks and fill in the number of ways each blank can occur if our problem meets the uniformity criterion. And that means every blank has the same number of possibilities regardless of what was chosen on the previous blank. Okay, here's what I'd like for you to practice on. Now some of these problems are going to be, some of them will be very straightforward, some of them are going to make you think. So make sure you come next time with questions. I've been concerned about the level of question asking that we've been having. So make sure that you're asking the questions that you need to ask. I can't help you if I don't know what to help you with. Okay? So, 7 through 10, 17 through 20, 27 through 29, 35 through 40, 45, and 46.